Okay, I've got two ramps here. We did something else earlier, but right now we'll just focus on quiz problem. The slopes are somewhat different. So we can estimate the time it takes this ball to get down the ramp. 1,001, 15, 15, 14. So it looked like it hit there right at 4. Now, if I start the two balls at the ends of the ramps at opposite ends, okay. Now you saw what happened. You can replay it if you need to. But everybody saw it. We did it 2 or 3 times in class. Looked like the balls crossed somewhere around the middle of the ramp. Well, ask you then to estimate the time down this ramp. Now, we got a time about 4 seconds in this, and people thought it was about 3 seconds in this ramp. So based on that, we're going to write the equations of motion for the two balls. Now here's our x-axis, and we'll line the, well, the meter stick wants to tip. Anyhow, we'll line the 0 up where the ball started here, where the center of the ball is at 0. And the center of the ball hits the end there at about 90 centimeters. So we're writing the equations of motion for this and this according to that x-axis. Both balls start from rest. And what ultimately we're going to want to do is set those two equations of motion equal and see where the balls actually should cross if your estimates were good. Now, we don't expect your estimates to be good down to the 10th of a second, okay? I'd say there's plus or minus half a second in my count and in any other estimate you might make. So I don't expect that you're going to predict that the balls cross right at the middle, even if that's what happened, which probably wasn't. Okay, then before that, while everybody's working in this, I'll just show what we did earlier. Trying to determine if the ramps were both straight. And we can't really determine that, but if we do this, release the two balls simultaneously here. Okay, that ramp going further from the camera looks faster. Looks like there's a greater acceleration. Now I switch the balls. It looks pretty much the same. Now if I switch this ramp, very similar, but balls are much closer together. And if I switch the two balls, kind of the same. Now, if I switch this ramp as well, okay, what do you conclude about the ramps? Are they both straight? Clearly not. If they were both straight, the balls would stay right together. So we're dealing with some uncertainty there. Okay, I've seen a lot of really, good looking homework. And some of them are especially good about, having the reasoning and so forth. Okay. I would expect from what I've seen that everybody would, or at least everybody that's done the homework, would easily be able to do this. Okay. Maybe there's some connections that we haven't drawn yet. One thing I do see in the homework is people using mystery formulas. V naught sine of 2 theta over G. Okay? Where's the cosine? Remember? Can you derive it? You're not working from the equations of motion if you're using those formulas. You really need to know how to work from the equations of motion or from the basic picture of a linear V versus T graph to deduce the equations of motion, or from an integral of constant acceleration to get the acceleration. Okay? If you're jumping to formulas that you don't totally understand just because they're easy to use, you're being an engineer, not a physicist. Engineers have to have access to thousands of formulas. Physicists only need about that many. Now, I'm not trying to make physicists out of you, but as an engineer, I take it as a given until somebody tells me otherwise, that the reason you're doing physics is so you can learn to do physics, not engineering. In engineering, you just grab whatever formula seems to work. You don't bother checking the units and just use it. Well, you darn well better check the units. Engineering or not. Okay, so we want to get in that habit. Most of you aren't writing units in your calculations, you're writing them all kind of fast. Okay, and you know, the reasoning process looks really good, but I'm thinking maybe you're looking too closely at examples or something else without doing the real work. I mean, you got to look at examples, but once you digest an example, then you need to be able to follow the process. Because among other things, when you have the test, you're not going to have examples from. You're not going to have every bit of knowledge you need sitting there at your fingertips. You're going to have to bring it out yourself. Okay? So in the first place, you can memorize those equations of motion, if nothing else. But preferably, you derive them. Now, let's see how that applies here. Okay? You want x1 of t and x2 of t. Well, in general, assuming uniform acceleration, velocity is a function of t, is an integral of a dt. Which is at plus an arbitrary constant. That arbitrary constant is going to be the velocity when t equals 0. So that if t equals 0, your velocity is your velocity at t equals 0. Now, we went over that first day or second day, I don't remember which, but very early in the course. And you need to lock that in. That's how you derive the equations of motion using calculus, which is the easiest way. But the trapezoid is equally easy. Still, we're looking for a position function, so it's easiest to reason this out from a couple of simple intervals. So we get this. Now we can apply it. All we got to do is figure out the acceleration. Well, you divide 90 centimeters by 4 seconds, you get the average velocity. You sketch yourself a little picture here. velocity starts at 0, the average occurs here, and the final velocity is double the average velocity. We get over that, explain it in detail. That's what you should be thinking about, not v naught sine of 2 theta over g or whatever. Okay, for cosine theta. You go back to the sum of two angle formulas for sine and cosine to figure which one it is. Can you derive it? Do that, but you really ought to be able to do it. You shouldn't be using it if you can help it, if you don't understand where it comes from. And if you can't work out the range of the projectile from the basic definitions. Stay close to the definition of rate of change to start with, and then the equations that come from assuming the rate of change of velocity to be constant. And of course, if it isn't constant, then you got to be able to do the inverse. Nobody's had any trouble doing those on the homework. Do you really understand what you're doing? Okay. So anyhow, well, that's going to be 45 centimeters per second divided by 4 seconds. Centimeters per second squared, okay? That'll be A1. Okay, so this is ramp 1. Actually, I haven't completed ramp 1, so let's complete it. So we know the acceleration. We know that V naught is 0. I'll just round off to 6.1 here. No, it's not 6.1, it should be 6.6. There's your x of t. And it's 1/2 that. So when t equals 4, you get 16, and 16 times 6 is like 90, and something's wrong. So that doesn't check out. So you got to check that out. Check this out. I think one of you got that, didn't you? The acceleration. So half the acceleration times t squared, half that, oh, that's 5.6. Okay, so now if t squared is 16, 5 times 16 is 80, 5.6 times 16 is 90. Okay. So I made a silly error there. And notice, I didn't just write this down and go on. I wrote it down and made sure that it gave me 90 centimeters when t was 4 seconds. Okay. Then I was relatively sure of it. And I just made a bonehead arithmetic error. Anyhow, there is my equation of motion. Now, ramp 2. Well, x naught is 90 centimeters. V naught is 0. V bar, if you wish, is 30 centimeters per second. Vf is 60 centimeters per second. Its acceleration is 20 centimeters per second squared. Now you reason all that out, you draw the picture and everything. If you're not drawing the picture, if you're not reasoning it out, you're going to be something on a test that's going to bite you hard. Okay? And you're not learning to do physics. You're just grabbing equations and plugging numbers in. Okay? And that's not doing physics. You want to understand a couple of principles because There aren't many formulas here, just you got to integrate the acceleration, get the velocity, you got to integrate the velocity, get the position. And if you got a straight line graph and start from zero, you can see that you end up at double the average velocity. Okay? That's simple compared to having to memorize about 30 formulas and use them right. Okay? Now, if you're really good at memorizing, you can get away with it. But I'm a lot less forgiving of using an equation improperly than of working from principles, because that's what I want you to learn to do. Okay? These principles that we covered like on the first day give us our two equations of motion. So now, two of t is 10 centimeters per second squared plus 90 centimeters, except I was careless in not putting the negative on these accelerations. Because the acceleration, our final velocity is actually, well, our displacement is negative, and that means the average velocity is negative and all that stuff. And your picture would look like this. For V versus T would be negative starting at zero, so we go like this with the average velocity here and so forth. Because we have a common x-axis, we're moving in the negative direction on that x-axis. Now, if t equals, and this is t squared here, one advantage you'll have, you're a lot less careless than I am. Okay. You do learn to be careful as an engineer. Okay, so there it is. It's kind of written badly. But if t equals 3 seconds, t squared is going to be 9 seconds squared. You multiply that with this, you get negative 90 centimeters plus 90 centimeters, which means the ball will be at x equals 0, which is here, which is where it was after 3 seconds. Okay? Now I've got the two equations of motion. Can you tell me where the balls are going to meet? I'll give you just a couple of minutes to work on that. Okay, so we're at a point where if you understand what you're seeing, which I think most of you do, I think everybody's pretty much doing the same thing. You just set the two position functions equal and solve for the time. Then you plug the time in to find the position and see that it's the same for both. So that's good, okay? The fact that you couldn't derive these wasn't as good, okay? Or that you couldn't solve the problem one way or another. I mean, you do have equations of motion. One of the equations of motion is x equals this, okay? Always 1/2 h e squared plus v naught t plus x naught. But that comes directly from the integration. So you don't have to memorize this. You can do those two integrations in about 10 seconds flat in your head. If you've used them several times, then you should be able to do that. Or you should be able to sketch that picture. And if you've done it half a dozen times, you can probably sketch it in your head and check that you're doing the right thing. Okay, well, one way or another, we set these two. So x1 of t is approximately 5.6 centimeters per second squared, t squared, and this one is negative 10 centimeters per second squared, t squared, plus 90 centimeters. So they meet when x1 of t equals x2 of t. Now that's simple enough. We got 5.6. It's actually, I think, 5.625. And I could do that, but that's probably not going to make much difference. So I'll just use 5.6. I really will feel more comfortable if you keep using units where they belong instead of slapping on the units you think. Because that almost always leads to serious errors at one point or another. Thank you, Brad. Okay. I'm not sure what he just did, but it might be my show. Okay. He's really quiet. I didn't know he was there. Okay. So we get this equation and we solve it. So I'm going to assume that your solution is right. Because it makes a certain amount of sense. Okay. So we get t equals 2.5 seconds. Now, really, the first ball took 4 seconds to get down there. It didn't take a half a second to get from here to here, probably more like a second. And that just tells us that our estimate of one acceleration or another, probably both, is a little bit off. And that's no problem because those were estimates. You can measure these things. And we will measure such things in lab and confirm. Okay? So we get t equals 2.5 seconds so that where that's going to be, oh, look at that. I didn't put my seconds squared on there. Seconds is squared, right? And 2.5 squared, 6.25. That's common calculation. You probably get used to if you aren't already. Okay, so I could estimate, it's almost like 6 times 6, which would be 36, but it's probably 4% low. So I'm going to say it should be 35 centimeters. That doesn't seem right, but let's see. Well, it's going to be negative 10 centimeters per second squared times 6.25 seconds squared plus 90 centimeters. Well, negative 10 times 6.25 is negative 62.5. You add that to 90, you get like 28 centimeters, okay? So something's a little off in the arithmetic, but you have reasonable agreement. And the balls didn't cross at 28 centimeters. I'd be back about here where the ends of the ramp are here and here. And that's simply because we used an estimate. I thought the estimates were reasonable. I couldn't come up with a more reasonable one. If I tried really hard, maybe, but it wouldn't have been great. But both solutions should come out the same, and they're different enough that I'm pretty uncomfortable. But work it out yourself. And maybe your 2.5 seconds was rounded off or something. Okay, because I just took what people got. And if I solve this equation, I'm getting like 4.4 centimeters per second squared, t squared equals 90 centimeters. 4.4 goes in about 20 times. And the square root of 20 is like 4.4, which is ridiculous. That can't be right. Oh yeah, it's 15.6. And 15 into 90 is 6, and the square root of 6 is more like 2.4 than it is 2.5. So I think it was 2.4 something, and that makes up the difference there. Okay, so check me on that. I just did those calculations very, very roughly, but I'm pretty sure it's between 2.4 and 2.5 seconds. If my working memory stayed with me long enough to do that right. And that's always a question these days, but okay. So do you understand how deeply you're supposed to understand this stuff by now? And how deeply you're going to have to understand it to answer the questions I'm going to ask you about what you saw in lab? Because I'm going to pose those questions this afternoon and want you to, I'm recommending you think about them for at least 15 minutes every day, rather than starting 15 minutes before they're due, which is not going to work for you. Okay. This stuff has to ripen gradually. You think about it, you let your brain settle, sleep on it, next day, it's going to be clearer. If you do that every day, you get some really good clarity. Okay, well, we're pretty much done with chapter 3 or chapter 4. Okay, so we have the projectile stuff. What if we had one ramp here, ball rolls down off right here, right? And falls to the floor in a parabolic arc. And another ramp here, where the ball rolls down to the end, falls off in a parabolic arc. Okay? Those balls going to collide? Can you manipulate the system so the balls will collide? Might be easier to have opposing ramps. They're only in 2 dimensions rather than 3. 3-dimensional problems really beyond scope of what I can ask you here. I mean, I could. I can ask you about anything, Answer this question based on Einstein's field equations. Yeah. Questions I couldn't answer. Okay, but I can ask them. Well, I'm not going to ask you those things. There are reasonable questions I can ask you, which is, what's the equation of this parabola? What's the equation of this parabola? And where do they intersect? That's just as simple as this. Because really, if this was one parabola and this was the other, just do the same thing. Okay? But not really, because you got to express the parabola in terms of x and y without 2. So you can figure out where they intersect, but then when is this one there and when is this one there? And are they there at the same time so they collide? And if not, well, let's move this ball a little further back here and see if we can make them collide. We might do that, and we might not, just depends on what else we get done. It's an interesting problem that I've never posed in class before, okay? Okay, well, as I say, you're going to see more questions on all that. Okay, the slope of this ramp, if we assume a level tabletop or shelf, whatever, is one inch out of about 35 inches. Okay, because actually the dominoes, which I just became aware of when I really looked at them the other day, are 1 inch by 2 inch instead of 5 centimeters by 10 centimeters. Now that's 2.54 by 10.08. Okay, I've always assumed it was 5 by 10 because somehow it's thinking metrically. As I started out measuring these thicknesses with a set of calipers in centimeters. So all my life, I've been assuming these were 5 by 10 centimeters, and they're not quite exactly that. Okay, well, anyhow, the slope of this thing is 1/35. Okay. Can you tell me what the angle with horizontal is then? Well, you can't necessarily, but can you tell me what the sine and the cosine of that angle are? We had a triangle. It's 1 here and 35 along the hypotenuse. That means the sine is 1/35. And it means the cosine is the square root of 1 minus the square of 1/35. It's using Pythagorean identities. So if you've got a slope, you can calculate the angle and then use the sine and cosine tangent if you need to, or you can just calculate the sine and the cosine from the slope. Keeping in mind, is it can simplify things. Why go to find the angle when you don't need the angle, you just need the ratios. Sometimes you need the angle. Of course, sometimes you know the angle, so you got to find the ratios and all that stuff. Okay, well, not quite sure. Well, anyhow, if we look at the stuff we did before lab, I'm just showing it to you again so you have a quick reference to it. And let's bring the camera back where it ought to be. Camera ain't moving. Got it upside down, but that's probably the reason. Okay. Now, I'd really like to find my white chalk. Some more. Ah, okay. There's a situation we looked at in lab. Okay. When I ask you to analyze the motion of the ball, you probably want to first make the simplifying assumption that since the slope isn't that great, that whatever speed you have here is in the horizontal direction. And since you know the range, you can figure out what the initial velocity should have been. But ultimately, you're going to want to be able to do it knowing what that slope is. Okay. And if the slope is 1/35, then your x velocity will be very slightly smaller than what you would think. But your time of fall will be just a little bit shorter because you're starting with some downward velocity. So you want to be able to analyze that. But you're going to get pretty good results if you just do the quick and dirty thing and assume that the initial velocity is in the horizontal direction without taking account of that angle. As it gets steeper, that becomes more of an issue. And it's a small issue, even at the slopes that we used. When you get up to the domino in the end, it is a difference that you might be able to observe. Okay, so make sure you understand from your measurements how to figure out how fast the ball is going. And I guess one thing you do need is you need how far the ball dropped. So I'm going to help you out with that real quick where I put my x-axis. Tables are 88 centimeters high. And the ramps are about a centimeter thick. Yeah. So you figure that the ball was at 89 centimeters above the floor. If you use these tables, not the ones in the blocks. That should be sufficient to calculate how fast the ball is going in each trial. And that's something you could probably put in a spreadsheet and do real quick after you've worked out one of them on paper. Does that make sense? So you work out the projectile motion for one of your trials on paper. Maybe for a couple of them, you want to get used to it so you can understand how to put it in a spreadsheet. But it's real easy to do once you understand the process. And since you got, a dozen calculations to do or something like that, I would recommend that you use a spreadsheet as soon as you're sure you know how to analyze the motion, okay? But it's simple. I mean, you know what the range is, you know how long it took to fall. Duh. Okay? When you get to the point where that's really done, probably need to think about it a little more, because I think many of you have been relying too much on formulas that don't tell you anything at the end. Okay? That's a universal tendency among physics students, okay? So don't feel bad, but try to go a little deeper than that. This thing about the pendulum, think about this because you're going to need to be able to do it pretty soon. This is directly relevant to what chapter 5 is, and we're really getting into chapter 5 now. We start talking about the forces. So what we've done here is we've said that the forces acting on this pendulum are a tension in this direction and a gravitational force that's not parallel to it. And there are no other forces. Now, if I was to bolt two of these things together, okay? So I got two of these things and I've got them bolted together, and then I turn one like this and put you at that end and me at, this end down here, and we pull on it. What's going to happen? It's going to straighten out, right? Which means that there's a net force that's causing this point of intersection to move. Now, there's not an exact analog, but this tension and this weight are going to tend to exert a force in this direction. And if this angle is small, this component of the tension will be pretty close to the magnitude of the tension, and pretty much equal and opposite to this, because you don't have any motion in the downward direction, which is a lie because the pendulum does go downward just a little. But if it's a small amplitude, its path is along a circle of much greater radius than the amplitude, so that, here at the bottom of the circle, most of the circle is pretty much along the tangent line. That makes sense? And I can draw that, so just to make sense of what I just said. Okay, so and it's a bad section of a circle, okay? Well, from here to here, the pendulum is just pretty much moving in the horizontal direction. There's very little vertical motion. So we can make the approximation that this force and this force are in equilibrium. What does equilibrium mean? It means zero net force. Okay? It's a little deeper meaning to it than that, but we'll talk about that later. So zero net force in the vertical direction because the thing is not accelerating in the vertical direction, which is the same as saying there's no net force in the vertical direction. If there's a net force in the vertical direction, there'll be an acceleration, because that's what Newton's second law tells us. Actually, that's what experiment tells us, Newton's second law embodies every experiment we've ever done in this nature. Okay, so philosophical points aside, thing ain't accelerating significantly in this direction unless you pull it way back and take a big old swing. Then it is accelerating in the vertical direction, and this model doesn't work as well. Still isn't all that bad. Okay. Now, if this and this are in equilibrium and this has a magnitude that's close to this, then this tension here is just equal to, well, the y component is mg, the magnitude of this is mg. What's this? That's the magnitude of this times the sine of, or the cosine of theta, right? So Tx is mg cosine theta. Now, what we do here, and I say Tx equals what? Well, there it is. And cosine of theta is approximately equal to, and I said cosine of theta. Theta's up here, it's the sine of theta. It's the opposite side, obviously. The sine of theta is x over L, right? I mean, there's a triangle with x here and L here, and a right angle here. Here's a triangle with the same angle because the tension acts along the string, and this represents the string, right? So we've got that. Well, understanding that reasoning gives you a good start on analyzing forces in general. And on the very first quiz I gave you, like on the third day of class, or not the quiz, the assignment I gave you after the second day of class, everybody worked in work and energy and forces, did a good job of it, okay? And I think you've understood that because you seem to have understood that all along, which gives you a good head start on chapters 5 and 6. Oh, then we get this differential equation. And if you're taking differential equations, you really ought to understand this anyway, for the sake of differential equations course, okay? Because it's something you're going to see in a much broader context. But it's simple, and I went over it in lab. But just quickly, the net force is mass times acceleration. If the net force is Tx, if there's no air resistance or anything, if things not oscillating in water, and you learn to do that in differential equations too, but we're not going to do it in this course. Your acceleration is going to be dx component divided by the mass. Well, magnitude of this is mg, so this is mg sine theta, which is mg times x over L. So your Tx is this, you divide by the mass, you get acceleration is negative g over L times x. It's not a constant acceleration because it depends on position x. So what we want to do is express the acceleration as a second time derivative of x. Okay, now you got to understand that's a time derivative, it's not the x. Second time derivative of x. And as we did in class, okay, what kinds of functions have second derivative? It's a multiple of themselves. Okay, well, it's just a sine cosine function of the exponential function. If it's a negative multiple of itself, it's got to be a sine or a cosine. The second derivative of an exponential function would be a positive multiple. Even if you got exponential of negative x, for example, you get a negative in one derivative, and then you get another negative in the second derivative, and you got a positive. Okay? So exponential function doesn't work, but sines and cosines do, and that leads us to this conclusion we'll talk a lot more about. And the square root of g over L we express as an omega, which we call an angular frequency in this case. Okay. And right there, you've got a big chunk of simple harmonic motion, which is kind of the last big topic that we study this semester, but we want to put things in that context because we use pendulums in L. Okay. And this is not hard to understand if you think about it. And if you understand it now, it's going to probably help you some different. So it's worth thinking about. All right, now we get this situation, which is the ball on the ramp. What do we have? We have a couple of vectors that look a lot like these. Okay. Now, explicate a board here. What happens to the ball on this ramp? Well, we know it accelerates in that direction. So we know that its motion is parallel to the ramp. So if we want to analyze the forces here, we're going to want to find the net force. What do we know about the net force? It's in the direction of the ramp. So what we do is we bring this into a diagram where we put I'll use the J vector. No, I'm not going to use the J vector because my coordinate system is not going to be our traditional coordinate system. Direction of the ramp. And that's the direction of your net force. Even if you have other forces acting, as long as those other forces don't cause the ball to be pulled up off the ramp, the ball will be constrained to move along the ramp, okay? Now, if I put a magnet up here, that might pull the ball up off the ramp because analysis won't be valid. Okay, so we got the negative mg here. Now, what's the direction of the force between the ball and the ramp? I can demonstrate that with a meter stick and a domino. Now, let's say that represents the ball on the ramp, and the ball on the ramp is actually bending the ramp down a little bit. Can you see that little bit of bend? Or maybe it's just compressing the matter of the ramp like a spring. But either way, if I release the ball, in what direction? If I release this tension, in what direction do you think the domino is going to move? That way? That way? That way? That might have been a little quick. Did it move that way, perpendicular? let me do it with a little less tension. I think I got it over zealous there. And on the video, I'm not sure that path would even have been possible. Apparently, we've confused Zoom. Now it's showing a different camera. I don't know what the heck it's showing. Let's see, I can see this. Okay, we've got a real problem here. I don't know what's going on with the camera. Okay, I can see the meter stick here. I haven't plugged this camera in. But the camera is picking me up over here, but there's the camera. And if I put this in front of the camera, it doesn't do anything. See, all of a sudden, it just lost the camera. Because that's this camera down here that we're picking up. So let me see if we can get the camera back. Camera's right now plugged into the HDMI port of my this has gone on far enough. The camera lost power? Maybe. It's a little loose over there. Okay, there it is. Okay, let me pull. Okay, there was an interruption. Turns out I finally figured out that the domino I launched went over further than I expected it to, and in the process of retrieving it, I pulled the plug loose on the camera, defaulted to another camera. So we finally got that straight. So I want to do this again because I pulled this thing way down and it went really fast and it was kind of hard to see. So I'm just going to pull this down, not quite as far. And we see that it went that way as well as up. So it's very plausible that the thing moved off perpendicular to the, excuse me, to the meter stick, and there's symmetry arguments that we could make and so forth that would make that pretty compelling. But the bottom line then is that this normal force is going to be perpendicular to the incline. Okay, so we've got, I guess you can't see it over here, but talking about the free body diagram with the ball and the incline, where the incline's at angle theta. Okay. Again, the ball is constrained to move along the incline. So the net force is in the X direction, according to the axis I've drawn here. We draw a Y-axis in this direction. The Y-axis being perpendicular to the X-axis, the normal force is in the direction of that axis. If we just have the two forces, the weight and the normal force, we can just sketch the components of the weight, which is negative mg. The X component of mg is just going to be this little vector, which is mg times the sine of theta, where this is theta. It follows from the fact that this is theta and this is perpendicular to this, that this being perpendicular, well, lose track of the perpendiculars, but just those facts that this theta is equal to this theta. Again, this theta is perpendicular horizontal. This theta is perpendicular to vertical. And I didn't say it right. This theta is measured with respect to horizontal. And vertical is perpendicular to horizontal. So this theta is measured with respect to vertical. So this theta has to be the same as this theta. And then it follows here. And also that mgy is negative mg cosine theta. Then, since we're constrained to accelerate along the x-axis, the net force perpendicular to the x-axis has to be zero, otherwise we'd be accelerating away from the x-axis this way, or away from the x-axis this way. These two forces are equal and opposite. It follows that F normal is plus mg cosine theta. And it's in the y direction. We could use I and j vectors if we wanted. Call this mg sine theta I. Call this one negative mg cosine theta j. And call this plus mg cosine theta times the j vector. General principle is that normal forces, contact forces of this nature, are perpendicular to the surface between whatever object is touching the surface and that surface. Okay, another situation we can have, if a force, one way or another, is being exerted this way on the ball, then call this force F for applied force. And here's your F. It has a component parallel to the x-axis and a component parallel to the y-axis. I didn't draw those quite right before. Okay. The component parallel to the y-axis is going to reinforce the component of mg parallel to the y-axis, so that if it's as represented in this picture, if the situation is represented in this picture with the applied force to the left where the incline is sloping toward the right, the component of F in the y direction is in the negative y direction. So the total force in the negative y direction will be greater than just the mg cosine theta we get from the weight. As a result, the normal force will be greater. And intuitively, that makes a certain amount of sense. Force in this direction is pushing back this way, but also pushing down a little bit into the surface, which means you're going to have more of a reaction in the surface. Okay. If this domino is here, and I'm pushing the domino, well, let's do it from back here, in. It's hard to move my hand around that way so that you can see what I'm doing. But if I'm pushing this way on the domino, it's pushing it into the meter stick a little bit, and also pushing it up the incline a little bit. So this force would have the effect of putting the ball into the ramp a little harder, and also pushing the ball up the ramp. This component of this force would push it up the ramp. This component perpendicular to that would push it into the ramp. Force that pushes it into the ramp, it increases the normal force over what it would be if this force is absent. I said it better when I was live, but the thing wasn't recorded. Okay. That should give you some sense of the kind of analysis that you're going to see in chapter 5. First two problems, the ones that are assigned for Wednesday, should be well within what you know how to do. The ones that are assigned past that, well, we're talking about the analysis on Wednesday, and hopefully prepare you a little better for doing those problems.